Welcome to TC online course on statistics on machine learning. In today's session, we are going to see the role of statistical thinking in machine learning problem solving. So in this session, we will explore how statistics forms the backbone of machine learning and how it helps the models learn patterns, handle uncertainty and make reliable predictions. We will also look at the real world case studies from healthcare and finance. Machine learning is often viewed as a magical black box, but in reality, every machine learning model is built on statistical reasoning. Statistical thinking helps us understand the data patterns, variability, and uncertainty. Without statistics, machine learning models would fail to generalize beyond training data. For example, a model trained only on city weather cannot predict rural patterns well. At its core, machine learning is about inference from samples. We collect data from a population, train a model, and infer the relationship between the dataset. Think of predicting student performance. We use past scores of all the students, attendance, and study hours as sample evidence to infer outcomes. Data is never perfect. Sampling bias occurs when training data does not represent reality. A famous case is hiring algorithms trained on biased historical data, leading to unfair rejection of women applicants. Statistical thinking forces us to question, is my dataset representative? Descriptive statistics in ML. Before modeling, we must explore data using descriptive statistics such as mean, variance, distributions, and outliers. For instance, in house price prediction, understanding the spread of prices helps detect anomalies like extremely overpriced homes. Machine learning models rarely give absolute answers. Instead, they output probabilities. A spam classifier might say 90% of getting chance of spam. This probabilistic thinking helps in risk sensitive applications like medical diagnosis. A key statistical lesson is that correlation does not imply causation. Ice cream sales correlate with drowning rates, but both are caused by summer heat. Machine learning models can pick correlations, but humans must interpret the causality carefully. Overfitting happens when a model memorizes noise instead of learning true patterns. Statistically, this is variance dominating bias. We prevent overfitting using validation sets, cross-validations, and regularization. So let us have a case study on healthcare diagnosis. In healthcare, a false negatives can be deadly. A cancer detection model must minimize missed cases. The confusion matrix helps evaluate errors: true positive, true negative, and false negative. Statistical trade-off guides threshold decisions. Coming to credit risk prediction, in finance, loan default cases are rare, creating class imbalances. Accuracy becomes misleading. A model predicting that no default always may still get 95% accuracy. Statistical metrics like recall and ROC are essential. Evaluation is statistical validation. ROC curve shows trade-off between sensitivity and specificity. Confidence intervals help measure uncertainty in performance. Hypothesis testing in statistics can confirm whether one model is truly better than another model. Statistical thinking supports responsible AI by quantifying fairness, bias, and uncertainty. Confidence intervals and subgroup analysis helps ensure models work equally well across the population set. So these are the key takeaways. Statistics is not optional in machine learning. It improves robustness, interpretability, fairness, and trust. A strong machine learning practitioner is always a strong statistical thinker. Now let us reflect that why is sampling bias dangerous? How does overfitting relate to statistic? Which metric is best for imbalanced data? These questions reinforce today's key concept. Thank you all for watching. Have a happy learning.
Thank you all for watching. We will meet you in the next session.